Okay, so now, if you remember, we talked about the derivative of logarithmic functions last time, and we got this formula. So I told you that this formula is in the version which is in the book, which is of course valid for all positive values for x, because ln x is only defined when x is positive. And I told you that this formula is not in the book, but you can immediately extend this formula to a formula which is valid not only for positive values for x, but also for negative values of x. And the formula is exactly the same. So it doesn't matter if you differentiate ln of x, it becomes 1 over x. If you differentiate ln of absolute value of x, that also becomes 1 over x. I want to teach the new lesson today, but before that, there is something which is, I think it needs to be completed from the previous lesson. Even though it's not in the book, I think it's good to know about this. So I will start writing this optional part here, if I can. Let me just write it here. So I would write optional here. But even though I call it optional, but I think it's an important piece of information. It's better you know it. If you go to your calculator, there are two buttons on your calculator. One is called log, which is the logarithm in base 10, and the other one is ln, which is the logarithm in the base of the Euler number e. But you also know about logarithms. For example, assume that you want to calculate the logarithm of 3, not in base 10. You want to calculate it in base 2. There is no particular button on the calculator that calculates the log in this base 2. So you need to know a formula how to do this, okay? So if we want to do that, we need a theorem. This is a change of base theorem for logarithm. Okay, so this you need to know. It's good. It's a very simple but very useful tool. So we have this. We want to have this formula. I want to show this formula for you. So if I have, so let me divide this into two pieces here now. Okay, so logarithm of a in base b can be written as the logarithm of a in another base c, provided you also calculate the logarithm of b in the same base and then divide these two numbers together. So if you calculate logarithm of a in base c, you calculate logarithm of b in the same base c, and if you divide them in this order, this can be simply, this is equal to logarithm of a in base b. Of course, you need to respect the conditions. So what are the conditions? A should be positive. B which appears in the base should not only be positive, but not equal to 1. And c, which also appears in the in the base, should also be positive and not equal to 1. If you respect all of these conditions, then the logarithm of a in base b can be written as the logarithm of a in base c divided by logarithm of b in base c. So let us not just memorize that. Let us see why this works. Okay, so what should I can, if I want to prove it, one way of proving it is just using the definition of the logarithm. So I would say let logarithm of a in base b be equal to some number m, logarithm of a in base c be another number n, and finally logarithm of b in base c be equal to p. we prove that what my goal is to show that m, which is this one, is equal to n over p. If I can show that m is equal to n over p, then I am done. Okay, we show that m is equal to n over p. Okay, but now when you say logarithm of a in base b is equal to m, what is the meaning? It means that if I write b to power m, it becomes a, yes? So this means that b to power m is equal to a by the definition of the logarithm. And when I say logarithm of a in base c is n, what do I mean? I mean that c to power n is equal to a. And finally, when I write logarithm of b in base c is equal to p, this means that c to the power of p is equal to b. Yes, so this is the consequence of my new naming, yes? But let us see, I want to find a connection between capital M, capital N, and capital P. So how should I do that? Okay, so here, instead of this B, I can put C to power P, yes? Because C to power P is equal to B. So I will take this B and put C to power P instead. Okay, so therefore, we have C to power P, and of course I have another power M. So you realize what I am doing. I am taking this out, and I am putting C to the P instead. But there is another exponent M, so I have to write it. It's equal to A. But instead of this A, I put C to power N because they are also equal. So this becomes C to power N. But on the left-hand side, I can write C to power P times M equals to C to power N. Yes? I have an exponent, another exponent, so I just multiplied. But here it's mentioned that C is positive and not equal to 1. So it's crucial. C shouldn't be equal to 1 because now I can conclude that if C is not equal to 1 and positive, and you are saying that these two numbers are equal, there is only one way this can happen, and that is when the exponents are equal. So this means that Pm is equal to n, and then if I divide by m, then it means that, sorry, if I divide by p, this means that m is equal to n over p, and then we are done. So actually you see that the proof is very, very simple. Of course, usually two versions of this formula are helpful. Usually it's common. One choice is to, of course, you can choose C whatever you like as far as it is positive and not equal to 1. But two choices are common. One choice is to take C to be 10. Okay, so then what does it, the formula will give me this. The logarithm of a in base b is equal to, in the numerator I will have logarithm of a in base 10. In the denominator I will have logarithm of b in base 10. But you remember the convention, when the base is 10, we don't write the base. It becomes logarithm of a, and that's exactly the button on the calculator divided by logarithm of b. So if someone wants to calculate logarithm of a in base b using the calculator, you can calculate logarithm of a log button, and then division button, and then another log button, yes? Button, yes? So this is the formula sometimes you can use to calculate the logarithm in a different base. And then of course another common choice is take C to be the Euler number. If you choose this one, then log of a in base b can be written as log of a in base e. E is the Euler number, divided by the logarithm of b in base e. but I told you that there is a convention that you don't write log of a in base e. The name is ln of a, the natural logarithm. So it becomes ln of a divided by ln of b. So another thing that you can do to calculate log of a in base b, use the ln button 2 times and the division button. Yeah, so that's also possible. So this is good to know about these things, because I think this is a very crucial point about logarithms, which is missing in the Swedish system. I really want you to learn about this. And then let me also talk about what happens if you want to differentiate a log function, not just ln function. Then I think you know what to do now, yes? So my point is, how can I calculate? By the way, let me write one consequence of this. Another interesting situation is that you take C to be A itself if A is not equal to 1, of course, yes? If A is not equal to 1, then let us choose C. Let C be equal to A this time. Then what happens? Then you will have log of A in base B is equal to log of A in A, because I have chosen C to be A. And then I have log of B in base A. And then what is log of 1? A in base A, it's 1. This is one property of logarithm, yes, divided by logarithm of B in base A. So that's also one very interesting formula. So if you have logarithm of A in base B, you can write it as 1 over, and then you interchange the role of these two. Take B up and A down. Of course, A shouldn't be equal to 1 here. That's also a nice formula to remember when you're working with logarithms. Okay. So you see that there is one formula, but there are 3 consequences which are important to know as a high school student. Now let me ask this question. So here you see that I have a formula for the ln of x prime. Ln is just a particular logarithm in which the base is equal to e. But what happens if I do not have the same base e? I have a different base. So what can I do? So the question is that, so if I have f of x equals to logarithm of x in base a, okay? And of course, I have the properties that x is positive, a is positive, a is not equal to 1, so that this function is defined in the first place. Now the question is that, what is the derivative of this function? So far, if instead of this, I give you this and I ask you the derivative, you know the answer is 1 over x. But now I can combine this idea of the change of base and the formula that we have here to calculate the derivative of, to determine the derivative of this function. So what should I do? I would write it in this form first. I would say that f of x is equal to ln of x divided by ln of a, yes? So why this is true? Because of this formula. Logarithm of a in base b can be written of ln of a divided by ln of b. Here I have logarithm of x in base a, so I wrote it as ln of x divided by ln of a. But this denominator, this is a fraction, but this is not a real fraction, meaning that ln of a is a constant, so 1 over ln of a is also a constant. And then I have ln of x here. Okay? But now I can differentiate it immediately because this is just a constant. So I don't need to do anything with that constant. A is a constant, so 1 over ln of a is also a constant. So I need to differentiate the function, but the formula is here. So the derivative of the function ln of x is just 1 over x. And then if you go to the books, we can multiply them. So it becomes x times ln of a. So let me also write this, but this part was completely optional. You see, this is at the level of your knowledge, but let me write it in this form. If x is positive, if a is greater than 1 and not equal to 1, then the derivative of log of x in base a is simply 1 over x ln of a. Yes, so this is something good to know. Yes, and of course the chain rule version is also clear. So instead of x, if I have a function of u, log of u in base a, then of course it becomes u prime divided by u ln of a, so which is always the case. So this is one thing that I want you to know, or I want you to know about this. So it's very natural to talk about this idea here in this point, at this point. Okay, any questions so far? Okay, let me go to the new lesson, which is a very important one. That's the product and the quotient rules, okay? So do you remember so far we had these rules? We know that if f is added to g, and I want to differentiate this.
I have a question.
Yes?
In the previous slide, if I could see, yes, there you wrote 1 divided by x times ln a.
Yes.
Under you wrote u prime divided by u times ln a.
Yeah, you can write. So I thought that it is clear. So let me explain if it is not. So in principle, you should write 1. Yes, but here u is a function of x. So then it means that you, according to the chain rule, you have to multiply by u prime.
Okay.
Yes, but then this u prime will go up. So this is why I wrote it quickly, sorry. Is that understandable now?
Yes.
Yeah, good. Okay, so far we have this rule, the sum rule, that if I have the sum of two functions, the answer, and I want to differentiate it, it becomes the derivative of the first one plus the derivative of the second one, and the same rule applies when I have the difference, so it becomes the derivative of the first one minus the derivative of the second one. We actually learned a very, very simple version of the product rule, meaning that if I have a function but not multiplied by another function, but that function is a constant function. This particular case we already know from Math 3C. Okay, so this becomes just c times f prime. Now the question is that what happens if this is not just a constant? If this is another function g, which is not a constant, okay? Okay, the first thing that I want to mention is that if you have f times g prime, you are not allowed to draw this analogy, to push this analogy further and say that, okay, because the derivative of the sum is the sum of the derivatives, perhaps the derivative of the product is the product of derivatives, which turns out to be totally wrong. Okay, and then the same thing for the quotient. If I have this, if you write f prime divided g prime, that is also totally wrong. Today we want to talk about what are the correct formulas for the first one and the second one. The first one is called the product rule. The second one is called the quotient rule. Okay, so in principle, let me write this with a different color. So this is the point. If I have the product of two functions, what is the correct answer for this? And if I have f over g and I want to differentiate this, what is the correct answer to this one? Okay. Okay, so because this is also mentioned in the book, let me talk a little bit about the proof, the way that we derive this formula. Okay, so the product rule first. So let me write the product rule. Okay, so let's say S of x be equal to the product of two functions f of x multiplied by g of x. We determine S prime of x. Okay, but you know the definition of the derivative. S prime of x is a limit. So it is the limit of S of x plus h minus S of x, and then divided by h goes to 0. So hopefully you know what to do here. So I just copy and paste these parts that I don't need to change anything. So these are the similar ones. And then I have a negative sign here. S of x is just a product. So I just write it the product. And then what is S of x? So I need to, I think, expand this a little bit. Yeah. So let me make it a little bit bigger. Okay. So here, what is S of x plus h? So it means that I need to replace the input of my function with x plus h. So if I do that, because I have two x's here, both of them have to be replaced by x plus h. So it becomes f of x plus h multiplied by g of x plus h, and then minus s of x, which is f of x, g of x. Yes? So, but you see that I want to find a connection between the derivative of this new function and the derivative of f and g. The algebra is not that simple as in the previous case. If you go to one of the previous videos, you will see that I have proven this for you. The reason that this was simple, because you see the algebra was simple. So making a connection between this formula and the derivative of f and g individually for the case of sum and difference, and this case is very simple. But here you need to be a little bit more creative to find this connection. I don't know. So let me myself continue that. So I would write this. This is given in the book. This is why I'm just emphasizing on this proof. So what we do something like this. I would write g of x plus h times g of x plus h. The first term I just copy and paste. Then what I do, I would write minus f of x g of x plus h, which was not there before. So I am subtracting this intentionally, but I have to compensate for that. So I have to add the same thing back so that I haven't changed anything at all. Yes. And then what you see here at the end, I also have this minus f of x g of x. So let me fix this one if I can do it properly here. Yeah, better. So let me explain again. You see, this term that I have subtracted, I have added also. So they will cancel, and what is left for me is this one, which I had it here, and also this one, which I had it. So I hope that you agree with me that this equality makes sense because they are the same thing. But what is the point here? The point is this. If I take this one with this one, I can factor a gx plus h out, and I can take these two and I can factor f of x out. Okay, then after factoring things out, you will see why this is helpful. So this becomes the limit. I take g of x plus h out. What is left for me is f of x plus h. From the second term minus f of x is left. Yes? And then from the second term, I factor f of x out. From the second pair, I factor f of x out. So what is left for me is g of x plus h minus g of x. Yes? And then I will have this divided by h. H goes to 0. Now, hopefully you realize why this is useful, because this combination divided by h is nothing except the derivative of f, and this combination divided by h is nothing except the derivative of g. So it means that I was somehow able to connect the derivative of the product to the derivative of these individual functions. But let me just change it a little bit. So I will write it in this form. I will write it as g of x plus h multiplied by f of x plus h minus f of x divided by h plus f of x, and then I will have g of x plus h minus g of x over h. H goes to 0. Yes, is that understandable? So what I have done, I have one expression plus another expression divided by h. So I have separately divided this by h, plus I divided this by h. But then I put this, instead of putting this in the numerator, I put this aside next to the fraction. So hopefully this is clear. Okay, here, this term is simpler, because if I ask you in the whole expression here, what is my variable, you shouldn't get confused, because the variable for the limit is just h. X is considered to be a fixed constant from the beginning, even though x is not a constant, but you fix it here and then start continue. You are talking about the derivative at point x, so it means that you fix x and then continue. So as far as this limit is concerned, x is a constant. So this is a constant, so I don't care, because it doesn't depend on h at all. It's f of x, a number. And the limit of this part, you know, the limit of this part is nothing except g prime of x. The limit of this part also, you know, is g f prime of x. But this also depends on h. So the question is that, what is the limit of g of x plus h when h goes to 0? Okay, so this is something that we need to answer so that we can do this. My claim is that this is also g of x. You might say that, okay, I send h equal to 0, this becomes equal, but this is not the correct statement. The reason that this becomes equal to g of x actually is because if the function is differentiable, the function is also continuous. Okay, so let me just tell you something here. This is not in the book, but I want you to at least hear the correct version. So if I want to calculate the limit of g of x plus h when h goes to 0, I do something like this. I will take x plus h to be a new variable h, x, capital X. When h goes to 0, this means that capital X goes to little x. Okay, and then what happens, instead of that limit, I can write the limit of g of capital X when x goes to x. But if this function is continuous, this becomes g of little x. So let me see, this is not always the case. Do you remember in Math 3C, I also a little bit talked about continuity. We say that the function f is continuous at a point A if the limit of that function becomes equal to the value of the function. This was the definition of continuity. If this condition holds, we say that f of x is continuous at that point. Now, why G is continuous? Because in this problem, we are assuming that G is differentiable. If G is not differentiable, we are not allowed to differentiate it in the first place. So when we are talking about the derivative of the product, we implicitly mean that these functions are differentiable. And there is a rule. If a function is differentiable, I already talked about this. These are very important concepts. If a function is differentiable, it's also continuous. So if the function is continuous, it means that I can write this limit. Okay, but this part you can totally ignore. This is not given in the book. But this is the correct version of doing that. So what I can say, this implies that this question mark is nothing except the G of X. Now let me rewrite everything. Forget about what I have written in the box. Let me continue with the blue color. So the limit of this part, according to this explanation, is G of X multiplied. The limit of this part is F prime of X plus this one is a constant, does not depend to the variable of the limit, so I will copy and paste it. And the limit of this part is nothing except G prime of X. Now, this formula is what is called the product rule. So you see, let me make it smaller. So it means that if you have a product, you want to differentiate it, you are not allowed to just take the derivative of the first one and multiply it by the derivative of the second one. It's a little bit more complicated. You take the derivative of the first one, but do not multiply it by the derivative of the second one. You multiply it by the second one itself, and then you do it the other way around. You multiply the first one itself by the derivative of the second one, and then you add the results. This is we call it the product rule. So I will write it here for you. So here we have, if f times g, I want to differentiate it, differentiate the first one, but multiply it by the second one itself. Oops, I don't know why this is this. Okay, so let me write it again. And then you will take the first one and multiply it by the derivative of the second one and then add them. This is called the product rule. Yes? Any questions so far? If you don't like the reasons, you can just totally ignore the reason that I brought this up, because I want you to understand, and it's also given in the book. But if you don't want to know the result, the ideas why these are correct, you can just learn how to use the formula itself. So this is what you need to know how to use, and the formula is of course given in the formula sheet, but you need to learn how to use it. Any questions so far, so that I can go to examples? Okay, so let me write this formula here. F times g prime, the derivative of the first one multiplied by the second one, plus the first one multiplied by the derivative of the second. This is called the product rule. Let me write the name here. The product rule. Okay, so example. So differentiate. So number one, here let me make a very simple example first. So f of x equals to 2x times x squared plus 2x minus 1. Okay, so assume that you want to differentiate this. This is something that Math 3C students can also solve. They don't have to use the product rule because there is a way out of it, yes? How can I do that? So let me write method 1. Okay, so I just want you to know this as well. So you see that if someone gives me this function to differentiate, I will not use the product rule, because there is a simpler way. I just multiply here. Yes, I will get 2x to the 3, and then I will get 4x squared minus 2x. And I don't even need the product rule in the first place, because I can immediately differentiate it. It becomes 6x squared, and then I will have plus 8x minus 2, and then the problem finished. But let us use method number 2, which you can also use the product rule right now. Yes, why I can use it? Because that's a product of two functions. So if I want to do it using this method, I would say, so let me write using the product rule. So f prime of x, according to the product rule, is the derivative of the first one. Let me be patient and write it once. The derivative of the first one multiplied by the second one itself, plus the first one itself multiplied by the derivative of the second one. Yes, and I have to continue until I do not have any prime left. So the 2x becomes 2, and I multiply it by x squared plus 2x minus 1. Then I will have 2x, then I have 2x plus 2, the derivative of the second one. Let me simplify to confirm that that's the same answer. I multiplied that, it becomes 2x squared plus 4x minus 2, and then it is 4x squared plus 4x. And if I simplify them, it becomes 6x squared plus 8x minus 2, and you see that that's the same answer. And you see that this is even longer. So this is why I'm saying that whenever you can avoid probably these formulas, don't blindly use them by brute force. Sometimes if you're a little bit patient to think about the problem first, you can solve it easier, even if you see that both of them gives the same answer at the end, but one of them is longer than the other one. But of course, sometimes it is inevitable to use the product rule. Okay, so let me give some of those examples. So number 2. So let me write f of x, a very simple function that you cannot avoid using the product rule. For example, x e to power x. I want to differentiate this. There is no other way. I have to use the product rule here. Okay. So hopefully you realize that you are not allowed to differentiate it and write it 1, differentiate it and write it e to power of x, and then multiply them and give me e to power x, which is wrong. You immediately realize, even though this is simple, but that's still a product. So I have to use the chain rule, okay? So how should I use that? Sorry, not the chain rule, sorry, the product rule. This becomes the derivative of the first one multiplied by the second one itself, and then the first one itself multiplied by the derivative of the second one. But the derivative of x is simply 1. 1 times e to power x is this one. And the derivative of e to power x is itself, so it becomes x e to power x. So you see that if you simply write this, it is wrong, because this is the correct answer for the derivative of this function. It's an example of a very simple function in which you have to use the product rule. There is no other ways out of it. Any questions? Okay, so we can, I don't know, we can cook up a lot of examples. We can combine different, so let me just give you 1 or 2 more examples. So what if we have this, for example, ln of x, a square root of x multiplied by ln of x squared plus 1. So we want to differentiate this function. Again, you see that that's a product, so I can use the product rule. it becomes the derivative of x is equal to the derivative of the first one multiplied by the second one itself plus the first one itself multiplied by the derivative of the second one. And hopefully so far you know that the square root of x is a famous function. I told you remember it separately, so it becomes 1 over 2 square root of x, and then you multiply it by ln of x squared plus 1, and then you have a square root of x. So let me write the formula if you have forgotten. Last time we learned that the derivative of ln of u is u prime divided by u. So this is the chain rule version of the derivative of the ln function. So this I have to take it u in my head, and then I can use the chain rule version of this derivative. So I will have this fraction line. In the denominator I put the u itself, and in the numerator I put u prime, but u prime is simple, so let us just do it in our head. So this becomes 2x. So that is the correct version of the derivative of this function. Any questions?
No.
Okay, so I think it's clear. You can also, of course, combine a lot of functions together. So some part might be, for example, let me just give you one more example and then we can switch to the next topic. So so let me write, for example, f of x is sine to the power of 3 x squared plus 1, and then I will have plus let me write it in this way. So sine to the power of 3x multiplied by cosine to the power of 2x. So we want to differentiate this function. So how should I do that? First of all, you see that that's a product. I want to differentiate it. So this becomes the derivative of the first one, but multiplied by the second one itself, plus the first one itself multiplied by the derivative of the second one. This is the new lesson, but what is coming after is just the old lesson. So you need to know how to differentiate this function first. Okay, so you need to take this one in your head to be u. Then you have u to power 3. If you differentiate it, it becomes 3u squared, but you have to multiply by u prime. But u is sine, so it becomes 3 sine squared multiplied by sine x prime. Let me write it in 2 steps. So this becomes 3 sine squared of x, but multiplied by sine x prime. And then after that, cosine squared x should be copied and pasted, okay? And the same story there. So I need to write sine to the power of 3x. For cosine, what I need to do, 2 goes down. It becomes 2 cosine x, because this is u2, but you need to remember to multiply by u prime. Yes? And there's one more step left. So if you remember, the derivative of sine is cosine. So this becomes 3 sine squared x cosine x. This becomes, sorry, let me write it in this way. This becomes cosine, but there is a cosine squared there. If I multiply them, it becomes cosine cubed. So let me just write them. There's no enough space here. And then the next one, let us see what happens. The derivative of cosine, if you remember, is minus sine. So this minus sign will be multiplied to this positive sign. It becomes negative. Oh, it disappeared. So this is minus sine. And then this sine multiplied by this sine is sine to the 4. I also have a 2, and then I will have a cosine. So it becomes 2 sine to the 4 cosine. And that is the answer, sine to the 4x, sorry, cosine. So you see that you can also combine the formulas. Any questions? Okay, but there is a natural question here. Can you guess what is a natural question here for the product rule? Okay, let me tell you something, by the way. Do you remember I told you that we learned a very simple version of the product rule? Yes, do you remember? This is also a product rule, but we never use the product rule. This becomes the derivative of the constant multiplied by the second one itself plus the first one multiplied by the derivative of the second one. But what is the derivative of a constant? It is 0. So this is totally gone, and what is left is CF prime. So when we have a constant, we really don't need to use the product rule. Even if we use it, it is correct, but we usually quickly write this. Okay, so first I want to mention that this is consistent with what we learned before. Okay, but there is also a natural question at this point. Isn't it clear what should be the question?
Is it commutative?
No. No, I mean the natural question, I talked about the product rule for two functions, but you might ask what happens if I have the product of three functions. Okay,
Isn't that
so yeah, I can, it's not commutative. Commutative means that you can interchange.
Ah, okay. Yeah.
Yes, if you mean it's probably the word close to it is associative.
Oh, chaining.
Yeah, so if you, that is, and by the way, that is completely normal to ask. Yes, for example, instead of having this function, I can have x times sine x times e to power x. It's a very natural question. How should I differentiate this one then? It's a product of three functions. But a product of three functions, according to associativity, can be always seen as the product of two functions if you combine two of them into one function. Yes, so let me just do it in the next page. So my question is now this. What happens if I have f times g times h, for example, and then I want to differentiate? So what can I do here? It's clear, as you said, that's associative. So f times g times h can be viewed as f times g as one single function times h. So for example, if I consider this capital F, then this, even though this is the product of three functions, but it can be viewed as the product of only two functions. And I already know how to do with two functions, so let us do that. F, G, H, let me write here, start from here. So I want to calculate f times g times h prime. But by this intermediate variable, by this auxiliary variable, I view the product as the product of two functions. So I can write capital F times h prime. But I know how to deal with the product of two functions. It becomes the derivative of the first one multiplied by the second one itself, plus the first one multiplied by the derivative of the second one. And now I replace capital F with this f times g, because f capital F was just a name. I gave it this to be able to solve my problem. So then it becomes f times g prime. You see, instead of this f, I put f times g, and there is a prime here, so I put the prime here, and then after that I have h, so I write h, and then plus, instead of capital F, I can again put small f times a small g, and then after that I will have h prime. So I wrote this here, and then I copied and pasted this h prime. But it is not finished here. You see here what I have is the product again. I want to differentiate of a product for two functions again. So what happens? It becomes the derivative of the first one times the second one plus the first one multiplied by the derivative of the second one. What I wrote here is the answer to this part, and then I have an extra h that I have to multiply. And then here, I don't need to put this pair of brackets. I can just remove them because it's product all the way around. So this becomes f times g times h prime. But if you don't mind, let me also multiply this h inside. So what happens? It becomes f prime g h. The second term becomes f g prime h. And the last term here, I just write it again. It becomes f g h prime. So you might be, you can guess the pattern, yes? If I have three functions, I differentiate the first one, but do not touch the second and the third one. The second time, I differentiate the middle one. I do not touch the first one and the third one. And finally, I do not touch the first and the second one. I just differentiate the last one. Okay, and I think that it is now clear for you what will happen if I have more than three functions, yes? So what if I have f times g times h times k, for example, and I want to differentiate this? It's clear now, hopefully. You differentiate the first one, but you do not touch any one of the rest. Then you do not touch the first one, just differentiate the second one and copy and paste the last two. And then you continue f, g, h prime, k. And finally, you can have f, g, h, k prime. Of course, if you really want to prove it, one way of proving this is mathematical induction. That's also a good exercise for yourself to show that this can happen for n functions, not 3 or 4 functions. So you start for n equal to 2. That is just the normal product rule. And then you assume that this is to be true for k number of functions. Then you show that this is also valid if I have k plus 1 functions. That's a good exercise to do, by the way. Okay, any questions? Let me just give you one example. So let me just give you that example that I started with. So assume that I have x times sine x times e to power x. So if I want to differentiate it, it becomes the derivative of the first one multiplied by the second and the third one, plus the first one multiplied by the derivative of the second one, and then the third one, and finally the first and the second multiplied by the derivative of the third one. But then this is simple. The derivative of x is just simply 1. The derivative of sine is cosine. The derivative of e to power x is equal to itself. And that is the derivative of this function. Any questions? Good. Now we want to talk about the quotient rule. For the quotient rule, even though we can again start from the definition of the derivative, but it becomes a little bit cumbersome to do this in that way, we can combine the product rule and the chain rule in a wise way so that we can find the formula for this. Okay. So let us see what we can do. So here, let me see how much space. Yes, I have enough space. So let s of x be equal to f of x over g of x. And then my goal is to find the derivative of s. Yes? Now, can you have an idea how can I use the product and the quotient rule to answer this question? This is given as a level 3 problem in the book. So I'm actually solving, I don't have the, I have the book here. No, sorry, I don't have the book here close to me. But this is a level 3 problem in the book. You are supposed to show this.
Rewrite the g of x. Oh, sorry. Go ahead.
May you please repeat?
We can write f of x over g of x as f of x times 1 over g of x.
Okay, then. But the problem is that, so you are partially correct. You can write it as f of x times 1 over g. The motivation behind that is clear because you want to benefit from the product rule. So you are interpreting this as a product. Of course, that's completely correct. But then what happens, if I want to use the product rule, I need to differentiate this one. That's okay. Multiplied by this one, that's also okay. But then I need to write the first one multiplied by the derivative of this one. So what is your plan for this part?
Rewrite it as to the power of -1.
-1, exactly. So let us combine these two ideas in one go, okay? So I would say that s of x can be written as f of x. Hopefully you agree with me that this is g of x to the power of -1. Everybody happy? So there is no difference between this way of writing s of x and the original one. But at least you see this. If I ask you what is this, let me see. If I ask you what is this, you would say it's a quotient. If I ask you what is this, how you read it, you would say it's a product. And that's good because I know the product rule. So let me just immediately start doing that. So s prime of x is equal to the derivative of the first one multiplied by the second one itself. Plus, plus the first one, the derivative of the second one. This is the product rule, yes? So the product rule. Okay, for the first term, let me write it back into the form of positive powers. So I will bring it back to the denominator, and I will write f prime of x over g of x. It's easier to write in this form. But for the second one, what is your proposal? Any ideas?
You use the chain rule?
Yes, how?
By taking g of x as the u.
Exactly. That's this. G of x is a function of x, so I call it u. And then I have u to power -1, then I have prime. So -1 goes down. U to power -1 is -2, but you need to remember to multiply by an extra u prime. Yes? It was behind my picture, I think. Could you see that? So I have u to power -1 prime. It is -1 u -1 times u prime. But this is minus u to power -2 u prime. So remember, -1 minus u to power -2 u prime. Again, it goes behind that. Okay, sorry. So it becomes, it's easy. Let me just write it. F of x minus u to the power of -2 times u prime. Yes? So let me explain here. -1 goes down. You have u to power -1, which is -2. But you need to remember to multiply by the derivative of the base because of the chain rule. So we are done. But this formula is not very symmetric to memorize. So let me write it a little bit nicer. That's the only thing that I want to do now. So this becomes f prime of x over g of x. And then what can I do here? First of all, if you don't mind, let me write minus from the beginning, because that's a product of 3 terms. One of them is negative, 2 of them are positive. So finally, the answer becomes negative. And then if you don't mind, let me take this one to the denominator as before and make the power positive. So it becomes f of x times 1 over g of x to the power of 2. And then I have g prime of x. But I can make it a little bit simpler. So let me copy and paste the first term. Then let me combine everything into a fraction. So here I have to multiply this by 1 by this. 1 doesn't have any role here, so it becomes f of x times g prime of x. And in the denominator, I have g of x squared. And now I can take the common denominator. So what is the common denominator? Is g of x squared. This is my common denominator, but this divided by this is gx times. I have to multiply this in the numerator. So it becomes f prime of x multiplied by g of x. And then I have a minus sign here. So I put the minus sign. And then the denominator of this one is exactly this one. So I don't need to change anything for that fraction. So it becomes f of x, g prime of x. And that is the final formula that you will also get it in the formula sheet, okay? So let me write it here for you. If I want to write a simpler version for that, I would say that f over g prime, you see how it reads. It is the derivative of the numerator multiplied by the denominator itself minus the numerator itself multiplied by the derivative of the denominator divided by denominator squared. So this becomes, if you want to remember it, f prime g minus f g prime divided by g squared. And that is called the quotient rule, yes? So the quotient rule. For the quotient rule, be very careful, because the quotient rule, as you see, is a little bit complicated formula. So what I told you before, if you remember, we had a long example with different parts. Some parts of it was including fractions. Even you could solve those problems even if you didn't know about the quotient rule. Still, I believe that that is a better solution. So some fractions are in a way that you can avoid using the quotient rule. So please go and review that example that we had in the very first few sessions when I was teaching derivatives. So those fractions, for example, one type of fraction, let me just give you an example instead of talking so much. So let me go to the next example. Differentiate. So number one, f of x, for example, equals to x to the power of 3 plus 5x squared minus 2 divided by, let me make it simple, for example, x squared. If you want to differentiate this function, of course you can use the quotient rule. This is why I want to solve this problem in two ways. But this is also a problem that I can give to Math 3C students in principle. But they need to be a little bit more creative. So I would say method one, which I prefer this one. So I mean, the old method that we learned is still preferable for this particular problem. So if I want to solve this, do you remember what we're supposed to do? What we are supposed to do? If I don't want to use
divide each term by
exactly. So that is still easier. So even if you can do it in your head, much better. So I would write x to the 3 divided by x squared plus 5x squared divided by x squared, and then minus 2 divided by x squared, and then you write it as x plus 5 minus 2, and you bring it up, it becomes this. And now you immediately and simply can differentiate. The derivative of x is 1, the derivative of 5 is 0, the derivative of the next term becomes positive 4x to power minus 3. And if you want to, you can put it back as the positive power, but it is not a necessity. You see, it's as straightforward as it is. But if you mistake, I wouldn't say it's wrong, but if you use the quotient rule, you are making life harder for yourself using the quotient rule. Yes. Okay, so here, if I want to do it, what should I do? I would say that f prime of x is equal to, let me write everything. Let me show the formula. Oh, I don't have the formula here. So let me write the formula quickly here. So if I have f over g prime, then it becomes f prime g minus f g prime divided by g squared. Okay, so if I want to use this formula to solve this problem, then it becomes the derivative of the numerator. So let me write it. Times the denominator itself minus the numerator itself times the derivative of the denominator, and then divided by the denominator to power 2. Yes. But then I have to continue. The derivative here is very simple. It becomes 3x squared plus 10x. And then I have a, yes?
In the denominator, you forgot the power 2.
Thank you, thank you. So it is 4. Let me write it here. Thank you. And then I multiply it by x squared. Then the numerator is at this one again, but multiplied by the derivative of x squared, which is 2x. And then, as you mentioned correctly, it is x to the power of 4 now. You see, the calculations are unnecessarily long. But of course, it will give you the final answer correctly. So let me confirm that. So I multiply this inside. So this becomes 3x to the 4 plus 10x to the 3. And then I multiply this by a minus sign on 2x. So it becomes minus 2x to the 4 minus 10x to the 3. That's positive 4x. And then I have what? I have x to the 4. But then you see that this one and that one are canceled, so I will get x to the 4. Yes. So this becomes x to the 4, and then I have 4x divided by x to the 4. Of course, you can just stop here, but to confirm that this is the same answer, I divide them separately. And then you immediately see that I am getting the same answer, but you see that this is completely tedious. So it's very important to know when to use this quotient rule. It always works, that's completely clear that it always works, but it needs more time to calculate the same simple problem. Use the quotient rule only for the cases which is inevitable. So you need to, by practice, you need to learn when it is inevitable. Any questions here? And to keep the consistency, let me try to see if it works to change the color. Yes, it might work, yes. Any questions? Okay, but let me just give you an example that you have to use the quotient rule. There is no other way. Of course, you see that the proof of the quotient rule, you can say that, okay, I don't use the quotient rule, I always use the product rule and the chain rule. But that's up to you, but I really don't recommend that. If you have to use the quotient rule, then please use it instead of going through the proof. Of course, if you do this way, that's also correct. Okay, so let me give you number 2. F of x, very simple functions first. You don't think it should be very complicated. No, a simple function as ln of x over x. Okay, so some of you might say that, okay, I bring it up, make it -1, and then I use the product rule. That's up to you, but I don't recommend you to do that. So here, if I want, I have to use the quotient rule. So I would write f prime of x is equal the derivative of the numerator multiplied by the denominator itself minus the numerator itself multiplied by the derivative of the numerator, of the denominator, divided by the denominator squared. The next step is that you need to remember or see the table in the formula sheet. The derivative of ln of x is just simply 1 over x. And then you multiply it by this x, which is already here. And then I have minus ln of x. And then in the denominator, I have x squared. But of course, if you want, you can also simplify. This x here and that x are gone, so I am left with 1. So this becomes just simply my 1 minus ln of x divided by x squared. So this would be the derivative of this function. So I can, of course, cook up a lot of examples, but I don't think it's that useful. You already know how to combine these functions. Any questions here? So here I don't think I have much more to say today. So we learned also about so I think everything is finalized now. So I think it would be good if I want to write everything in one place. Yes. So what we have learned so far, let me just summarize this. All of this information that I am writing will be given to you in the formula sheet. So we have this situation, we have our function here, its derivative. What we learned is a constant function, its derivative is equal to 0. We then learned that x to power c, it becomes c x to power c minus 1, is c is a constant. We learned e to power cx, c goes down, I repeat the function. For a to power cx, we learned that c goes down, I repeat the function, but I also have to multiply by ln of a. And then we learned about the derivative of sine function, which is cosine x. We learned about derivative of cosine function. It was just minus sine x. And then we learned about, oh, sorry, I remember that I had to say something. By the way, now, do you realize what is missing in this table? So let me, pardon?
Tangent of x.
Yeah, exactly. So that is what I remember that I had to say something. Okay, so let me put an empty space there. Then I have the ln of x. The derivative is 1 over x. We learned that one as well. Now, we also learned some generic rules. If I have f plus g prime, it becomes f prime plus g prime. If I have f minus g prime, it is f prime minus g prime. If I have a constant times f, it becomes cf prime. If I have f times g prime, it is f prime g plus fg prime. And then if I have f over g prime, we have f prime g minus fg prime over g squared. And then if I have f of g of x, the chain rule, totally prime, it is the prime here multiplied by g prime of x. These are generic rules that we learned. So let me change my color here now. I also told you what happens if you have ln of absolute value of x. This is not mandatory to learn, so this becomes again the same rule, but here x shouldn't be, sorry, let me clean this. But here x shouldn't be equal to 0. Here the only constraint is that x should be positive. So the second one is more relaxed. Yes, I also told you what happens if you want to differentiate this log of x in base a. So you will get 1 over x ln of a. So these are not mandatory, of course. Okay. And then I told you what are the consequences of these formulas. I told you it's better to remember them separately. So I have x prime, which is 1. Then I have 1 over x prime, which is minus 1 over x squared. and we also have square root of x prime, which is 1 over 2 square root of x. These formulas are not given to you here. They are needed, of course, but you need to always find them if you don't have them in your memory. Okay, and for this one, e to power x prime is just e to power x. E to power minus x prime is minus e to power minus x. So that's also something we know. Okay, so now let me, hopefully can draw this line here. And it does not that's acceptable. So this empty space now, this is the last function that we put in. So that is of course, a very natural question. We know about sine, we know about derivative of sine, cosine, so it's natural to ask what's the derivative of tangent. But let me just do it here, hopefully if I have enough space. Yes, that's enough. So let me write the derivative of tangent of x. But I think you know how to do that, yes? How should I do that?
First we change tangent of x into sine x over cosine x.
Yes, and then I use the quotient. Exactly, thank you. So let us do that. So the derivative of tangent of x prime is equal to sine x over cosine x prime. And then it's become the derivative of the numerator multiplied by the denominator minus the numerator multiplied by the derivative of the denominator divided by the denominator squared. But we know about the derivative of sine. The derivative of sine is cosine, but cosine, another cosine multiplied is cosine squared. And then the derivative of cosine is minus sine. Minus sine multiplied by another minus sine becomes positive sine squared over cosine squared x. So let me do it in two different ways. Of course, one easy way is to write 1 over cosine squared, which is very clear because cosine squared plus sine squared is 1. But this is also sometimes useful to do it a slightly different way. What I do, I separately divide this by that and then divide this by that. Okay, so it becomes cosine squared x over cosine squared x plus sine squared x plus over cosine squared x. The first one becomes 1, the second one becomes tangent squared x. Both of them are very common. So I would write here these formulas. So the derivative of tangent of x, what is written in the book is 1 over cosine squared. But especially if you go to university next year, you will see that this is also very important to remember that this is equal to 1 plus tangent squared of x. So it doesn't matter which one you use. Of course, this is more compact way to use. So I also prefer myself this one, but sometimes it is good to remember at least this combination. And there is also a name, if you remember. So let me put this with different color. It is called secant squared x. So if I want to tell you what is secant, if you remember, this is called 1 over cosine x. And then let me also write this cosecant. It doesn't need to learn them. It is 1 over sine x. And there's also something called cotangent. Cotangent is cosine over sine. It's the reciprocal of tangent. This is just for extra information, so you don't need to know them.
Babak, I have a question. Will we get the table to the left and the formulas?
So everything that I have written here, you will get except this one and this one, which is not in your lesson, not this one. But these are, you will not get them, but you have to know them. But if you don't remember them separately, every time you have to start calculating them. But what you see here, you will get in the exam, in the formula sheet. Okay, any questions? Okay, so just let me give you an example of tangent and then we are done. So if I ask you what is the derivative of tangent x multiplied by let me write it. It's just multiplied by e to power x. So let me write e to power x on the left, and I want to differentiate it. So what I need to do, I need to write the derivative of the first one multiplied by the second one itself, plus, because that's a product, the first one multiplied by the derivative of the second one. But the derivative of e to power x is simply e to power x itself, and the derivative of tangent, we just learned that it is 1 over cosine squared x. And that is the end of this lesson.